Welcome back at C-Squared. In this video clip we're going to talk about limits, and we're going to start with this definition of a limit, which is known as epsilon delta definition. And this statement here means limit when x approach to c of f of x equals L, which means when x is getting closer to c, the function's getting closer to L. That you can see in this picture. When x is getting closer to this c, the function is getting closer to this L. And let's explain what is the meaning here of these two statements. If x is on one of these two intervals and getting closer to c, the distance between that x and c is less than delta. You notice this is delta, and this is delta, or greater than 0, and greater than 0 in fact. While that happens here for the x, look at here what's happened with the f of x, right? F of x will be in this one of these two intervals, and the distance between this point and L will be less than epsilon, because this is epsilon. That is the meaning of this epsilon delta definition. And let's see how we use this epsilon delta definition. We have here a limit given to us, limit when x approaches to 1 of 2x plus 1 equals 3, and we need to find delta such that absolute value of 2x plus 1 minus 3 less than 0.1. This is epsilon. So for a given epsilon, we need to find a delta. And you'll notice we're going to do the math and we're going to get this delta. We're going to get something like this. So we're going to start from what? From what is given us here, which is absolute value of 2x plus 1 minus 3 less than 0.1. I'm going to eliminate the parentheses first. 2x plus 1 minus 3 less than 0.1. And I'm going to have 2x minus 2, right? Less than 0.1. Then I can factor out the 2. And inside of parentheses, I'm going to have x minus 1 less than 0.1. And then one of the property of the absolute value is you can pull the number outside the scalar, and we have 2 times x minus 1, and we don't need the parentheses in fact, less than 0.1. And the last thing we can do here is divide by 2, and we end up with x minus 1 less than 0.05. This is delta. And I want you to see that in this picture, which is, I zoomed this area of the function 2x plus 1, and you notice this is delta. For this delta of 0.05, we have this epsilon. And in fact, I should say backwards. For an epsilon of 0.1, we have a delta of 0.05. 0.05 is the largest value of delta that will guarantee us this statement I start from. Any other smaller value of delta will also work for this problem. Let's move to the second example. In this example, we're going to use again epsilon delta definition, and we want to prove this limit. So it's a little bit different than the other problem, but it's kind of the same math. You will see. The meaning here is that for an epsilon greater than 0, you'll be able to find a delta greater than 0, such that absolute value of 2x plus 1 minus 3 is less than epsilon. So if we're going to do the same math, we're going to end up, if you remember, with 2 times the absolute value of x minus 1 less than epsilon, and we're going to have here x minus 1 less than epsilon over 2. That will be the delta. So we have a correlation here between epsilon and delta, and we notice for an epsilon greater than 0, we get a delta greater than 0. Whatever epsilon you have, you divide by 2 when you have the delta. And that is the idea of this problem. There are, most of the time you are not going to use this definition, epsilon delta definition. You're going to have to find the limits, and there are three ways: numerical, where you use table, graphical, or analytical way, and I'm going to show you that using the next example. Here we have to evaluate this limit, and I'm going to use first the numerical way, which means you take these values 1.9, 1.99, these values, and you replace where x is. So if you do that for the first one, if we have x equals 1.9, I'm gonna do f of 1.9, and that will be 1.9 minus 2 over 1.9 squared minus 1.9 minus 2. And if you evaluate this expression, you're gonna end up with 0.344. Let me put that here. Okay, if you do similar for the next one, for this one, you will get 0.334. For the next one, you're gonna get 0.333, and you will notice this value repeat when you go on the other side of the table, and I'm gonna explain you in a moment what do I mean by the other side. Okay, so this we have the same value. So what I mean by the other side, you notice these two, this is this number you see on the left of 2 are smaller than 2, right? 1.9, 1.99, and 1.999, and the other side of the table the number are greater than 2. So we go closer to 2 from the left side and the right side. So let's see what's happened when you go closer and closer to 2 from both sides. You notice we go closer and closer to the same number, 0.333. This is the limit. The limit when x approaches to 2 of this function is 0.333. You can see that in the picture also. When we get closer to 2 from left and right side, we get closer to this value of the function, of course, which is not easy to be read in a graph. And the last thing I'm going to show you here is the algebraic way, which probably is the safest way most of the time. So we have limit when x approaches to 2 of x minus 2 over x squared minus x minus 2. So the first thing you do when you have a limit, you take the value and you plug it in. And in this case, you'll notice you get 0 over 0, which is called undefined form. You cannot divide by 0, but 0 over 0 is undefined form. And whenever there is a limit, you have to be careful because you may have a result. Okay, let's see how we do that. One of the technique is factoring. So x minus 2 is nothing we can do to factor out, but the denominator we can factor out, and that will be x minus 2 times x plus 1. And you notice now x minus 2 is gone, so we have here limit when x approaches to 2 of 1 over x plus 1. Again, I'm going to take the 2 here and plug it in, and I have 1 over, it's x plus 1 here, 2 plus 1, and that is 1 over 3, which is 0.333, right? So now we know the limit when x approaches to 2 of, I'm going to call it this f of x, is 1/3. And you see here the three ways. Like I said, the best one is the algebraic way. When you can use it, use it. And in this one, the algebraic way is factoring. Let's take a look to some special trigonometric limits. This is the first one. Limit when x approaches to 0, sine of x over x equals 1. you can see the picture here. I'm going to use this graphical way. When x is getting closer to 0, left and right, the function is getting closer and closer to 1. And the same for the second one. You notice when x is getting closer to 0, the function is getting closer to 0. Those are two important trigonometric limits. There are moments when the limit does not exist, and you notice here the three cases. You need to be careful of that, and you're going to see example in my channel. And the last part is when we have limits at infinity. This is what we see here. Limit x approach infinity of f of x equals L. Look at here, when x is getting larger and larger, the function is getting closer to L. X is getting larger and larger. The function is approaching that horizontal asymptote, if you remember, something like that. We have a similar statement when x is getting smaller and smaller, approaching negative infinity. You see the function is getting closer to L. And that's it. If you enjoyed this video clip, don't forget to click the like button and come back on C-Square for more help. Thank you.